and thanks for the very kind introduction. So, I'll keep an eye on the time. Okay. Yeah, actually, so today is a good chance for me to introduce my work on the company memory design for AI. Basically, so the so basically, sorry. So basically, this talk includes two parts. The big part, the first big part, is the introduction of the focus paper, the ISSCC paper in three years ago, and so the story never ends. So after that, I have developed other works for AI accelerators based on our SRAM sim and RAM sim, and also including near memory computing accelerator for reinforcement learning. If you are interested, you can refer to our paper later. So let's go to the first part, the introduce of the focus paper today. So first is the motivation. Um, so we have witnessed the development of the fusion of computing units and memory unit. So there are majorly like three parts or three steps to develop those AI accelerators. The first is the ASIC design for the CMOS accelerator for AI. So especially this is work of Iris. We can see that if we look at the energy we transfer from the off chip to the on chip of only focusing on the weight transfer, you can see that compared with the computation energy cost, the Mac energy cost, it's about 200 times to six times of computation energy, and after that we have new technologies. We can do a near memory computing. It means that we can move the processing to the side of memory chip, and in that side we just lower the energy cost to transfer the weights or the parameters of the AI models from originally the 200 times to six times to the 55 times to six times. So the six times is on-chip data movement using the SRAM. And of course, we have an ideal case is in-memory computing. The in-memory computing means that once we load the parameters into the chip, and we can reload it again and again, and we don't have to use any additional energy to transfer the weights. So that's why we got a zero to transfer the weight here. So this is the ideal case. And what we want to do is the in-memory computing. And so this is the dream. And to realize dream, we can to realize this design, and we can see some challenges of our design. So the first one is, so we have just concluded challenges into three parts for this work. So the first part is the large computing circuit area. If we want to fuse the computation and memory, the storage function, we have to add additional circuits into the originally the memory micro. So basically, we can either put the ADC beside the build cell array, or we can just put some digital like shift add and add a tray onto the chip to fulfill this function. But in realizing this new circuits, the in-memory computing circuits, we can see that the overhead of the additional computing circuits is really large. Even it is even larger than the memory array itself. So this is the first challenge. So the second challenge is we can see that what we have done a lot of computing memory design, but all of this computing memory design is for the VMM, the vector matrix multiplication, and we just do the MAC computation. And actually, we will see later my subsequent works that we have a lot of new applications. We have various purpose of using this computing memory design. So therefore, the circuit design has to fulfill some various functions. For example, the and or all of the other bitwise computation instead of only the matrix multiplication. And third challenge is the DN deployment. Of course, the hardware design is fixed once we have designed and tip out the chips, but we have encountered a lot of different structures and different AI models. So when we deploy those AI models onto our chip, we will see that there are a lot of weaknesses of parameters onto the chip. So which results in a really low utilization rate. So like on the right hand side, this figure, usually we may encounter more than 20% of bit cells. So they are just they're there, and we cannot use it because of the structure and the deployment. So this is the third challenge. And toward this three challenge, we have developed three technologies. So I will introduce this one by one. Basically, this is an entire macro design, and we just split it into three parts. So the first one is the overall architecture. We call it ADC-less vector Hadamard product architecture. So a Hadamard product operation means that we just do the vector matrix multiplication element by element, and after we have done the element-wise multiplication, we just sum it up afterwards. So basically, we just split the VMM into two steps. The first step is fulfilled in the array, in the bit cell array, as well as the compute circuits. So therefore, we have to simplify the function, and we can get a smaller area and smaller design overhead for this computation. Of course, the computation form is also changed. We can see this structure of the macro design. So in the middle, we just split all of the bit cells into different parts. We call different parts the different compartments. So there are a lot of compartments there. So it's just composed of different parts of bit cells. And around it, it's the normal memory circuits like Bitline decoders and MUX, and the memory mode rewrite circuits, the write drivers, the the sense amplifiers, and also the revised Verline drivers we will see later, and post-sum circuits for the VHP computation, the e-memory computing circuits. And all of the circuits also work in two modes. So the first mode is the memory mode. We can load the AI model parameters into the macro, and then we can do the computation directly in memory. So this is the second computational mode. And this figure shows why we call this Hadamard product architecture. So on the top of the figure is the physical architecture of the circuit, and on the bottom of the part is the computation. So we just, as I have said, we have just split the VMM into two parts. So the first part is the vector Hadamard product. It means that the vector X times a matrix times the matrix W, and it just do the element-wise multiplication. And after that, we can add each column together, and we can get a row vector. So this has become a result of the VMM. So basically, this is the idea, and we can see when we do this operation, we can just emulate the step of this operation and design the circuits. So each circuits include the different compartments, and each compartment include different groups of these bit cells and RLPU, the reconfigurable local processing units. So it's a circuits. So let's look at one group of these circuits. So that's the second part. So inside so the circuits inside a compartment. So this is what's inside one compartment. So basically, this is the bit cells, and bit cells just store the AI model weight parameters here. And after that, we can just get all of the bill lines, the positive and negative bill lines into a four transistor structure circuit. And this circuit, we just call it RLPU. And because this circuit, this four transistor circuit just do all of the in array logic computation. And so on the right hand side, so this is a more clear diagram for this circuit. So these are the SRAM-based cells. So each row has a one bit. So in each column, and after that we add a in array four transistor circuits called RLPU to do the computation. And after the computation, we have another pull-up circuit, pull-up transistor here as a DCC. So basically, it's a sense amplifier to read out the computation circuits. The computation only do one bit, and so the only do the one bit logic operation. So let's show how. Let me show how it works. So basically, each time we just select one row of bit cells in each compartment, and so this is only show one column. And for each column, the data stored in the bit cell, the 1 and 0, is going into the going into the two transistor gates out of the four transistor, and another input will just will just connect to another two gates of the four transistor. And we can see this is basically the half part, the pull down network part of a AND gate. So basically we can just configure to an AND configuration and do a bitwise AND. Basically it's a bitwise multiplication in this part. And so for the operating principle, so first we just so first we just doing so control the phi, the gate the gate of the pull up transistor here to make a pre-charge. So to make a pre-charge, and we can make this aware of a DLO to the high voltage, and after that the computation will happens on this ILPU circuits, and we'll do just an AND. And after that, we'll just do a discharge using the DCC transistor here and do the computation. So basically, this is the principle of the dynamic logic. We just do the pre-charge and discharge to do the logic computation. And one trick here is why we design a four transistor here to do this is because we want to make a reconfigurability for the bitwise operation. So if we just do a different combination of the inputs, so connecting the two gates of the RLPU circuits, and we can get different logic operations. So yeah, because of time limit, I will just I will not show it one by one. But if you just calibrate all of the inputs and output, we can just do an AND or an XOR computation. For an AND operation, it's basically the bitwise multiply, and for an XOR, basically it can be basic part for the floating point of the sign bit, and for the OR part, basically it can do data mask. So it can support different logic operations and subsequently the different more complex computing functions. So this is the idea. And with this circuit design, we can see that the DCC, the pull-up transistor works as the ICA for the computation. Basically, it's a one transistor structure, so it's very compact. So it's just save the area, and also the dynamic logic is compared to the static logic. It's a biased design, and so it has a very good amplification function. And one possible weakness of this circuits is the leakage hazard diagram. It means that if we do the dynamic logic, if we pre-charge and we just leave it a longer time, so the charge we have the charge we have going into the pull-up circuit might just disappear. But our measurement shows that so this is not the case because if we want to avoid this leakage hazard diagram, we have to we have to limit the computation latency into its kind of into this so it's 0.6 microseconds. So this is really a long time. Basically, we just do the computation is normally just like tens to hundreds of nanoseconds. So this is okay for the circuit design. And yeah, if we have seen the structure inside each group, we can just form each column of the RPU plus the bitwise circuits, and we can form each compartment. And we just copy paste each compartment. So in the row wise. So therefore we can get entire the entire micro design. And the third part of this design is the post-sum circuits. So let's see the circuits after we just done the bitwise computation in memory array. So the post-sum circuits, so as a name shows, it's just do the sum up. So the sum up needs a because it is a bit serial operation. So we need a shift and add circuits and adder tree to add all of the elementary modification together to achieve the addition. So and we can form the entire vector matrix modification. So let's see these circuits. So basically, it's just shift add and adder tree. And towards the application of CNN, especially the depthwise convolution of depthwise convolution. So we have just revised the adder tree. Instead of we add all of the 32 outputs together, we just make each group of 9 outputs together. We just do sigma 9. It means that just add 9 output element together. And because we have 32 outputs, so therefore we can make it into a three group of sigma 9, and we still can make a sigma 4, so make another 4 element add together. So we just revise this adder tree into a split group design. So while we do this, we can show it in this very quick diagram, so example. So for example, for the depthwise convolution, so if we have a 3, so this is normally we have 3 channels of RGB, and for each channels, the parameters, the kernel parameters, we just need to load into the complete in-memory array. So first, so if we don't have this adder tree together, we have to do the 9-element sum up. So first way is we just store all of the 9-element group by group in one column or in one row. So in that case, we have to operate 3 times. So each time just add the 9-element together. So another way is just if we want to increase the parallelism, and we can just load all of the parameters into 3 column or 3 row, depending on what you define. And in that case, we can just do 1 operation a time to get to the 3 channel results. But in that case, we have to leave a lot of zeros there because we only need to add 9 element instead of the 32 element together for each time. So, but if we have this revised technique for the adder tree of sigma 9, so we can just get the balance of so we can use 1 operation and do the 3 groups of outputs. So that's our that's a basic idea behind this circuit design. So this is the small trick of the adder tree here. And so this is the major results of the utilization rate. And if we deploy the depth-wise convolution into this into our design sim macro, we can get a boost of this utilization rate, both in spatial and in temporally speaking. And for the measurement, we just do all of the Schmoot test. And we have a it seems like because the time is over. So this is the measurement results, and this is the energy efficient and throughput. And the comparative results is we just on the form factor, our design is really compact design because we just changed the ADC into the bitwise operation. And for the function diversity, we just support AND, XOR, and OR different logic operation as I've shown. And on the computing efficiency, so basically it's a compact design and it show a relatively high computing energy efficiency. And so this is the summary of so this work. And I also want to, I'm sorry, but I want to spend 1 more minute to introduce my other works, the following works, because the work I have introduced is 3 years ago. And so in this recent 3 years, so first we have developed a Verilog behavior models for the PIM macros. So if you are interested, we had released all the associated open the SOC open source project. You can just check around with our Verilog RTL using the PIM and the customized CPU. And the second is the SRAM sim. So for the probabilistic computing, so we just developed a SRAM sim macro and processor design for the MCMC sampling. So this is basically this is designed for the hardware infrastructure for the probabilistic AI. If you're interested, we have published our paper on TX1 and HPC recently, and also the RAM. So I also have done the RAM design for the universal Ising machine. So this is RAM-based design with novelty with a novel encoding scheme. So it's published in the Nature Electronics last year, and also the near memory computing for the reinforcement learning. So this is basically a FPGA design and the software toolkit for the RL for the reinforcement learning acceleration. And so yeah, so that's it. And if you're interested, you can refer to our recent papers, and also there are 2 QR codes for the GitHub and also our demo video. Yeah, so I'm open to any questions. Thank you. That's all.
Thanks. Please.